Bernstein and Tanya Lange talking about SafeCurves, their new mechanism for choosing safe elliptic curve cryptographic curves.
Thank you very much.
Thanks. So, a few quick words on, am I audible? Okay. So a few quick words on public key cryptography, so where elliptic curves fit in there. So SafeCurves, the curves stand for elliptic curves in there. And that is part of public key cryptography, so something that you use when you're signing, say you're a government, you're issuing e-passports, or CA, you're issuing certificates, or you're doing code signing. If you do that, then you're using public key cryptography and elliptic curves and RSA and also Diffie-Hellman signature, well, fine field-based signatures, DSA, are typical examples. Also, public key encryption, so when you're making a connection to a website, the first thing you do is you do a handshake. Well, assuming you do the proper thing with HTTPS, the first thing you do is you make a cryptographic handshake, and you have met the web page before, so you're building up a shared secret based on public key cryptography. RSA is also an encryption system, then elliptic curve Diffie-Hellman and normal Diffie-Hellman and fine fields are typical examples. And this is to be contrasted with symmetric cryptography, which you use for, say, bulk encryption. So if you do your full disk encryption, you don't want to do public key encryption because it's much slower. So AES and SALSA 20 are examples of a system where both parties, you and the hard disk, or you and the website that you have now shared a key with, know the same secret and then can transmit, encrypt the data very, very quickly.
All right, I'll give this one a try. So within public key crypto, why are people moving from RSA to elliptic curve cryptography? The main reason is because of an attack strategy called index calculus. Now, this is a complicated attack. It's something which keeps getting more and more sophisticated over the years. It started in the 1930s, before crypto was really understood. In the 1930s, people were thinking about how do we factor big numbers, and they started with the beginnings of index calculus. And then, well, okay, after that, in the 70s, people were still thinking about factorization. There's a CFRAC algorithm. And then suddenly, the late 1970s, there was the original Diffie-Hellman public key system and RSA. And that attracted a lot of attention to how fast can we factor numbers, how fast can we compute discrete logs. And people started really developing this index calculus idea. A lot of the buzzwords are listed here, like the linear sieve, the quadratic sieve, the number field sieve, the function field sieve. I should mention that some of these recent, the last few lines in this history listed here, for the function field sieve, that's not something which helps for factoring. It's only for discrete logs. But it's still within this index calculus umbrella. It's something which is a really terrifying attack algorithm. If you're trying to figure out how big do your RSA keys have to be, then you have to get into understanding this really complicated series of algorithms, and you have to worry there's going to be more improvements.
So to give you a numerical example of how smaller your security level gets, if you fix your key size, say RSA with 1024 bits or 248 bits, then in the initial, when they designed the system, they understood CFRAC, and the linear sieve was just coming out. So these systems for CFRAC would have a security level. It would take an attacker 2 to the 120 operations to break it for the smaller system, and 2 to the 170 for the bigger system. Now, when RSA was designed, the linear sieve has just come out, so that reduced the security to something like 2 to the 110, which is still pretty big. So RSA 1024, where the government now tells you don't use this anymore, at that time looked like 2 to the 110 operations. It's independent of the computer architecture. This is just mathematical operations. If you go for say, bit operations or computer instructions, it's a multiple of that. But then the algorithms just then mentioned have brought the security down to something like 2 to the 80 or to the 112, depending on the size of your RSA key. In the middle of this, even before the number field sieve came out, Victor Miller was proposing to use elliptic curves. So there was a Crypto 1985 paper where he proposes use elliptic curves, and one of the arguments he gives for this is that mathematically it doesn't look like there could be anything like these index calculus attacks. So closest to elliptic curve cryptography would be, say, Diffie-Hellman and fine fields, and there's an extensive use of making, well, your fine field look like the integers. There's some sort of, it's called lifting, and Victor shows that, okay, lifting wouldn't exist for elliptic curves.
All right, so to get an idea of what elliptic curve crypto looks like, we actually have a little warm-up here with the simplest kind of curves you can imagine. Well, you could maybe think about straight lines, but okay, if you don't have a straight line, maybe the simplest curve you can imagine is a clock, or mathematically a circle. So this is x squared plus y squared equals 1. Take all the points x comma y in the plane that satisfy x squared plus y squared equals 1. That's the unit circle. Now, I have to give you a warning here, which is that circles are examples of ellipses. Ellipses are stretched circles. And you might think when you hear elliptic curves, that's just another name for ellipses, but that's not the situation. Ellipses and circles are not elliptic curves. Elliptic curves are just a little bit more complicated than circles. So when I show you a circle, or if I stretched it, made it an ellipse, that would not be an elliptic curve. And any advantages that elliptic curves have, ellipses and circles don't have that advantage.
Okay, just in case somebody has forgotten what these things look like, it's kind of quaint, you know. So some examples of points on the clock. So when you look at this well, pocket watch, then you find the 12 o'clock points up there. So in mathematical coordinates, we have 0 in the x direction, and we have 1 in the y direction. So this is a circle where this top point up here, we say it's at 1, and this one is also at 1. And then there's more points. There's, for instance, the 6 o'clock point at 0, minus 1. There's a 3 o'clock, the 9 o'clock point. And then we get into like our goal, where exactly is the point that is 2 o'clock. So we go like somewhat over and then somewhat up. The up is just a little bit, the over is quite a bit. So when you compute those things, then the up is by 1/2 and the over is by square root of 3/4. And then, well, coming up with more numbers. Once you have one of those points, you can mirror it. For instance, you can flip the x and y. You go 1/2 in the x direction and minus 3/4 in the y direction. So, okay, 1/2 in this direction, minus 3/4 down there. So we find the 5 o'clock point. And there's lots of other points that make nice times. And then there's other points. So if you're just looking for x, y that satisfies x squared plus y squared equals 1, then also this point 3/5, 4/5 is a point. I mean, if you go to enough decimal places, you can approximate this as a time, but it's not a regular time on your clock. And then there's also the ones with getting the plus or minus sign. I mean, it's just x squared, y squared, so if you have x, y, you also have minus x, y, x minus y, and so on. You can flip also x and y, and you can find many, many more points.
Okay, so what happens when you add times? For instance, if you look here, P1 on that picture is something like 1 o'clock maybe, and P2 is something, well, a little more than 2 o'clock maybe. Maybe P1 is like 1:15 or so, and P2 is like 2:30 or so. And if you add those, then you get something which is like past 4 o'clock. And then, okay, I promise there won't be a whole lot of trig, but just for this slide, just a little bit of trigonometry, that once upon a time, everybody learned formulas for how to do addition of angles on a circle. Yeah. Now, long time ago. In math courses, for some reason, people, instead of on the clock, you start with 0 or 12 is at the top. In math courses, for some reason, they put 0 on the side. So the sine and cosine, you might think, are kind of flipped from what you might remember from the trig courses. But, okay, if x is a sine of an angle and y is a cosine of an angle, then there were these formulas for adding them. And this will be about the nastiest formulas we give you in this presentation. So sine of alpha 1 plus alpha 2 is sine of alpha 1 cosine of alpha 2 plus cosine of alpha 1 times sine of alpha 2. And there was something similar for the cosine. Now, we'd like to simplify this and not think about sines and cosines. We'd like to just work with points on the curve, x's and y's on the curve, and not have to think about angles. So to simplify this picture a bit, to do clock addition, again, exactly the same addition operation, but just working with x's and y's. Down at the bottom there, if you say the sines are x's and the cosines are y's, and just replace all the signs, like sine of alpha 1, call that x1, and cosine of alpha 1, call that y1, and same for x2 and y2, then you have some formulas for just doing some multiplications and additions and subtractions at the bottom there. The sum of 2 points, x1, y1, and x2, y2, is x1, y2 plus y1, y1, x2 down at the bottom there, and the y coordinate is y1, y2 minus x1, x2.
Okay, to give some numerical examples, we already know some points on the clock, so we know the 2 o'clock point and the 5 o'clock point. And if any sane person asks you, okay, what is like 5 hours after 2 o'clock, then you answer 7 o'clock. Similarly, our addition should take the 2 o'clock point and the 5 o'clock point. So in numbers, is this square root of 3/4, 1/2 for the 2 o'clock point, and the 1/2 minus square root of 3/4 for the 5 o'clock point. And then we use the formula as I then just said, and we come up with, well, this result, and that's indeed 7 o'clock. Now there's also that at some point you're going to wrap around the clock. So if you have a 5 o'clock and 9 o'clock, well, makes 14. In Europe, that's all right. Here, I learned that you say 2 o'clock to that. So in mathematical formulas, we again put in the 5 o'clock point, the 9 o'clock point. The 9 o'clock point is actually very nice because it has a 0 there, so everything you multiply by y just magically disappears, and we get, indeed, the 2 o'clock point. And then there's also these weird points, the 3/05, 4/5, and we can also toss those into this addition formula. We can compute 2 times the point, 3 times the point, 4 times the point, and so on. There's also, I already mentioned the 9 o'clock point being somewhat special. There's one point which is very special, namely the 12 o'clock point. If I ask you what's the time after 1:30, 12 hours later? Well, it's 1:30. So adding 0,1 to anything shouldn't change the value. So if you add that, then you get exactly the same xy that you put in. And you can verify this with the formulas. You plug in the x2 being 0, so that one is 0, this one is x1 times 1, that's all right, so it's x1, and here you have y1 times 1 minus 0, so nothing changes. Similarly, if you want to add the point on this side of the clock to the point which is at the same height of the clock but flipped over to the other side, so it has the same same y coordinate, same height, but the x coordinate has flipped the sign, then that is like 2 o'clock plus 11 o'clock. 10 o'clock, sorry. So then
Block arithmetic is hard.
So then you get the 12 o'clock point. And also, again, that works with the math formulas.
Okay, in crypto, instead of working with real numbers like the square root of 3/4, we want some finite thing that we can represent with a limited number of bits inside the computer. So instead of using real numbers, we use integers mod sum prime, or as the mathematicians like to call it, finite fields. So here's another picture of a clock. It doesn't look like that continuous picture before. There's only, well, something like 8 points on that picture. Yeah, it doesn't look like that, sorry. But there's still, okay, I should say what's going on in the picture. So this is integers mod 7. So when you add numbers and you get something 7 or bigger, subtract 7 from it. Like 3 plus 5 is 8, which is the same as 1. And when you multiply numbers, as an example down at the bottom, like 2 times 5 is 10. That's bigger than 7, so subtract 7, you get 3. If you subtract numbers, 2 minus 3, that would be minus 1, and you can add 7 to that and get 6. Minus 1 and 6 are the same thing. So we have only 7 different numbers we can work with, 0 through 6. And you can multiply these, you can divide, except for dividing by 0. Well, you saw before, like the 5 plus 9 was 14, which is the same as 2. And that's another example. That would be mod 12. Here I'm working with mod 7. Mod 7 has the advantage that you can divide by anything except for 0. So coming back to the picture up there, 0 is in the middle of the picture, and then it goes 1, 2, 3 over to the right, and 1, 2, 3 up, and minus 1, minus 2, minus 3 over to the left. And if you look at the top right of the picture, that would be 2 over and 2 up. And that's a point on the circle, because if you take 2 squared plus 2 squared, that's 4 plus 4, which is 1. So that 2 comma 2 is a point on the circle, which is why it's plotted there. And okay, if you plot all the points on the circle, it's the 8 points that are shown there. So that's a clock mod 7.
So a larger example, if you take a clock for 1,000,003, then, okay, at first you have to find a point, but once you have one point, you can happily start doubling it, and then, okay, you double it again. Now, one thing you notice, at the beginning, those numbers still stay small. So the reduction modulo this very large number here doesn't kick in. I mean, all we're doing is we do some squaring of these coordinates and some squaring of that coordinates, and we multiply and add those. So the numbers don't quite reach the prime there. But then you do 8 times and you do 16 times, and then you notice, aha, you've wrapped around. You've hit this equivalent to mod 12 on the clock or mod 7 in Dan's small example. And then, for instance, you add the point to it, I've so far just doubled. Now I'm going to add to it and say, okay, 17 times the point is this result, 951,405, and whatever y coordinate belongs to it. So this we call scalar multiplication. So you take a scalar, 17 in this example, and we take a point, that's the point, well, 1,000, 2, and they compute 17 times this point. And the easiest way is, well, we double and then we add a few times. Then it's going to show some more details about that. So scalar multiplication refers to taking n and p and computing n times p.
Okay, so the example you just saw is an example of the binary method of figuring out n times a point. Even if n is huge, it can be hundreds or thousands or millions of bits, and you can still do n times a point, where you say, okay, if you want n times a point and n is an even number, like 16, you start by computing 8 times a point, and then you double that. So you do 8 times a point and then add that to itself, and you get 16 times a point. And that'll really quickly get you to big powers of 2. If you have an odd number, then you figure out, say, 17 times a point by doing 16 times a point. And, okay, that doesn't make much progress in how big the scalar, the integer is, but most of the time you'll be doubling. So you do lots of doubling, some number of additions, and you really quickly get up to whatever size of n times p you want. So it's really, really fast. If you're given a curve point p, and you're given an integer n, you want to compute n times p, you can do that really fast. But what's really hard is, suppose you're given a curve point p, like an x comma y, like this 1,000, 2, and you're given the result of doing this scalar multiplication. Would you have guessed like that 951,405, if somebody tells you that, and the 877,356, would you have guessed that that's 17 times the original point? Yeah, here's another example where we took some 6-digit number. Okay, there's only a million possibilities. Your computer can do this real fast, but can you figure out some 6-digit number n so that n times 1,000, 2 is 947,472, whatever it is? It's doable, but it's much, much slower than just doing 30 applications of the point addition formulas, which is all we had to do to multiply that n times a point.
So here's why we care about this, or why you should care about this, namely cryptography. Now, I'm doing clock cryptography, which you maybe haven't seen in your computer yet, but let's stick with this example before we move on to something more complicated. So, if Alice and Bob know how to compute on the clock, and now all of us know how to compute on the clock, we can design a scheme where we can find a shared secret just by doing public computations, and some secret computation, but that stays on your computer. So, Alice chooses some big integer a, where big means, well, smaller than this prime that you wrap around with, but pretty much that size. Bob does the same, he also picks this integer, but they don't communicate this integer. Now both of them on their computer, preferably offline in a safe, whatever Faraday cage around them, do computation. Alice does a times the base point, so the point x, y that they agreed on, and Bob does b times this point. So each of them does a computation using the method that Dan just explained. So check whether it's even, then double. If it's odd, then, well, add, and so on. So now both of them have computed a scalar multiple. This scalar multiple looks like this. We don't know exactly what integer went in there, so it's hard to find what a and b were. And now Alice and Bob are comfortable sending these points, the resulting points, over the internet. So let me give you a picture for that. So Alice picks a, computes a times the point. Bob takes b, computes b times the point. Now they exchange those messages. Alice sends her point to Bob, Bob sends his point to Alice, and then there's another step where both of them do a scalar multiplication. Alice now takes her secret scalar a times Bob's point. Bob takes his scalar b times Alice's point. Now what we've done here is we've computed the point plus b times, and now that whole thing a times to itself. That's on Bob's side. So Bob has a times b times the point, and Alice has a times b times the point. So both of them, even though they changed the order of the computation, have gotten the same point. So this would be the shared secret of the two of them, and then they should, say, run it through a hash function, and they can use it for AES in some authentication version, so ASGCM, say. Now, if you're going to implement this, don't just pick any prime. Several primes or fine fields in general are bad for this. Also, Dan already said that clocks are not elliptic. So whatever sizes you hear for elliptic curves, they do not apply for clocks. So to get a good security for a clock, say you want to have RSA 3000 bits, then you have to choose a prime which has about half of that many bits. So if you're aiming for RSA 372, then you should have a prime with 1536 bits.
Okay, something else to watch out for, even if you've chosen a good prime, chosen a good, well, we'll tell you how to get around the second problem, like chosen a big enough prime, but we'll tell you later about elliptic stuff and how you can make everything much, much smaller and faster, and not vulnerable to index calculus. There's still another problem, which is timing attacks. So remember the rules for if you want to compute n times a point, then it depends whether n is even or odd. You get different results depending on whether n is even, then you do some doubling operation. If n is odd, then, well, you're doing some addition, and that changes the pattern of operations you're doing. So that, well, certainly the number of operations you're doing, the time that you take, is going to depend on what your secret number n is. Now you might think, okay, it's just, okay, there's some number of additions involved, like 30 additions in the example before, or, well, however big n is, maybe it'll be hundreds of bits, and then maybe it's 287 additions. And somebody who's listening to your computation, watching how fast you respond to network packets, they're going to see that total amount of number of bits that are set somehow in n. But is that really a lot of information? Well, it might not sound threatening until you realize that the same kind of side channels where people can see the total time often lets them see much more detailed information about the time you're spending on each operation. So, for instance, your computer, when your CPU is looking up bits of n, doing a memory access, then it's doing a certain operation, and that consumes a certain amount of power, and then that has your capacitor, which is feeding into the power supply, that winds a little bit. When your computer is doing some arithmetic, like it's doing, well, the multiplications from before, then it's doing something which consumes a different amount of power, and that makes the capacitor whine a little bit differently. There was a paper a month ago about acoustic attacks, where somebody had this cool setup, parabolic microphone, and then a target laptop about that distance away. And then with this parabolic microphone, in about an hour, they were able to retrieve a PGP secret key, well, from GNU PG. They were able to get a GPG secret key out of the laptop, just from the acoustics of the capacitor that was feeding the power of the CPU. The amount that was generating of noise was giving them side channel information about the secret numbers n. So if you want to avoid this problem, you have to, instead of using something where you're doing branches based on the bits of n and other variable time operations, you have to make sure you're doing constant time. Every single operation you do, you should not have any data flow from your secret integers to the operations that you're doing. Always the same operations. You can do arithmetic, like additions based on secrets, but not anything like an if or different cases based on secrets.
Okay, ready for elliptic curves? Okay, so here is one method of getting elliptic curve. You take a circle, you take a clock, imagine it like a shmoo ball, and then squish in the corners. So instead of having x squared y squared equals 1, you take a little bit away from it. And then, okay, to make the mathematicians happy, let's take some number times x squared y squared. This thing is an elliptic curve. Now, we've seen how to add points on an elliptic curve, but the elliptic curve has just one on the right-hand side. This case is a little bit different, so you can't just take exactly the same formulas, but it's very, very close. So this is exactly the addition formula that you had for the x-coordinate on the circle. This is exactly the addition formula you had for the y-coordinate on the circle. And then there's some bits in the denominator. Change it a little bit. So for comparison, here's the clock again. So the clock just has the x1, y2 plus y1, x2, and we have the same value up here, and then divide by 1 minus minus 30, so the 30 from up here, and then x1, x2, y1, y2, and then also in the y coordinate there's a denominator which is almost the same except for there's a sign flip. Instead of minus 30, it's plus 30. So if you're comfortable with the addition on the clock, then the addition on the elliptic curve looks almost the same. No, it doesn't work anymore with the angles here. So if you look at this angle plus this angle, it doesn't really add up to the angle to the red line. But other features are preserved. So if you add the 12 o'clock point to anything, it doesn't change anything. So if you add 12 o'clock to any point on the elliptic curve, just the same as on the circle, it doesn't change the value. This is what mathematicians call a neutral element. It doesn't do anything, like chemically neutral. It's actually a good thing that it doesn't work with addition of the angles, because addition of the angles would be a too simple operation. It's something which, again, fits like in the case of index calculus tags. So we're happy that it's not that simple, but we're also happy that we have the clock on the other side, which is very, very similar, and so we can use it for explanations.
Okay, this 30 is not something special. So there's lots and lots of elliptic curves out there. All you have to do is change the 30 to some other number, or the minus 30 to some other number. But I'll put in one little warning note here, which is that you want that number, the minus 30, to be something that's not a square. So here's the setup for serious elliptic curve crypto. You take a big prime p, and then you pick some integer d, mod p, which is not a square, mod p. Now, that's something you can figure out whether d is a square, a fast computation. And then the elliptic curves we're working with here, these are called Edwards curves, or more specifically, complete Edwards curves. It's any curve x squared plus y squared equals 1 plus d x squared y squared mod p, where again, d is not a square, mod that prime p. And then the addition looks, well, just like the addition we've heard about before, a little more complicated than the clock, and that minus 30 changes to plus d.
Actually, you should be wondering at this point, there are denominators. Isn't this a problem? Could you fall into a case where you divide by 0 and the universe explodes, or you get a sigfold?
Universe exploding is bad. Don't do that. But fortunately, you can prove that these denominators never end up being 0. No matter what the x1, y1 on the curve are and the x2, y2 on the curve, you'll never end up dividing by 0 here. So those denominators end up being always non-zero, and because p is a prime, you can always divide by any non-zero number mod the prime. So we refer to this addition law as being complete, which is kind of the normal situation. It's weird if something is incomplete, except, well, you'll hear more about exceptions in a moment. It's critical for this, for the denominators never being 0, it's critical that that d is chosen to be a non-square. You could imagine, wait a minute, suppose we take d to be a square. Is that going to be an elliptic curve? Yes, it is. And you can figure out what addition means on an elliptic curve. And actually, the same formulas seem to work. You can try implementing crypto where you've chosen d to be a square, and it'll look like elliptic curve. Well, it is elliptic curve crypto, except sometimes there will be divisions by 0. You'll never find those if you're just randomly testing, but an attacker knows how to find those. And okay, if you know what you're doing, you can figure out the exception cases. If you actually want elliptic curve crypto to work correctly when d is a square, then you've got to write quite a bit more code, and your test framework looks like much more of a mess.
Okay, so here's an example of some nice curves. We figured that when we distributed the slides that Dan shouldn't be the one talking about nice curves, and watch out when you Google for that. So this is a safe example of a very nice curve. If you want to use something for cryptography, this is something we recommend. So as a prime, you choose a prime with 255 bits. So the prime is 2 to the 255 minus 19. You can check this one is prime. And then for the d, it's a value. Then I don't like your setup. And for the d, it's a value which, okay, if you compute the fraction, it actually gets pretty big, but if you keep it as a fraction as these two values, it's not too big. This thing you can test is not a square in the integers mod to this prime, and then the curve x squared y squared plus equals 1 plus this d x squared y squared is a safe curve for elliptic curves. Everything we know, this curve is good. There are more nice curves. For instance, you keep the same p and d, and instead of having plus x squared, you put a minus x squared there. And then also at the plus dx squared y squared, you put a minus dx squared y squared. When you look for how to compute on those curves, having a minus in front of the x square is actually a nice feature. It's something which gives you an extra speed up, so if you care about speed, I mean, for this talk we care about security, but if you also care about speed, you might want to have the minus thing there. Now, is this also a nice curve? Well, it's the same curve. If you take your x and y, and you multiply any point on the first curve, you take the x coordinate and multiply it by square root of -1, which you can find exists in that fine field, then the x squared gets a -1, and the plus dx squared y squared also gets a -1. So every point on the first curve gets translated to 1 point on the second curve, and vice versa. So whatever you do on the first curve, you can also do on the second curve. There is a difference for arithmetic. One representation might be faster than the other. In this case, the second one is a little faster than the first one. But if anybody had any attack on one of those two representations, it just carries over. If anybody knows how to get Alice's secret on the first curve, that person just takes the second curve, multiplies x by square root of -1, and is on the first curve.
Okay, some more examples of elliptic curves. If you want to read the different standards out there for using elliptic curve cryptography, then you have to memorize all of these shapes. There'll be a test right after the talk. Yeah, you've seen Edwards curves, and then this thing with a minus is an example of twisted Edwards curves, where you have something in front of the x squared, which doesn't have to be -1. There's Weierstrass curves, where that's v squared equals u cubed plus something times u plus something else. There's Montgomery curves. We have something times v squared equals u cubed plus something times u squared plus u. There's all sorts of ways to view these curves as being other curves in disguise. Like the example you just heard with this -1, square root of -1. You can take any Edwards curve, for example, and if you do some little transformation on the x and y, you can turn that into the Montgomery curve. So you can take any Edwards curve and look at it as a Montgomery curve. There's other relationships that aren't always true. Like it's not true, for instance, that you could take any Weierstrass curve and look at it as a Montgomery curve or an Edwards curve. So there's restrictions, and you have to look at all sorts of details to see how these curve shapes relate to each other.
Okay, so then Weierstrass curves. You know, when people talk about when they were young and all these old people were saying you have no idea how good you've got it. You know, when I was a kid, we had to walk to school carrying our siblings on your shoulders, uphill both ways, and additional Weierstrass curves look like this. This is one addition. Actually, it's an addition with lots of cases. You're getting 2 points. All you want to do is just add those. Think of the pizza pieces on the clock. Think of the 2 points on the Edwards curve. This is what you have to do when you're implementing Weierstrass curves. You first have to check, does it happen so that the first coordinate, the u coordinate on this curve, happens to be the same? Well, if not, then we are in this branch. And then things are kind of easy. Okay, it's still lots of operations. But to add those 2 points, we compute something lambda here, which is the difference of the v coordinates divided by the difference of the u coordinates. Then we have to square the thing, subtract the first u and subtract the second u, and we know those two things are different, so okay, fine. Then we compute the v coordinate, and finally we're done. However, should it happen so that the v coordinate was non-zero? If the v coordinate was 0, then we're in a different case. If it happens so that the u coordinates are the same, meaning you're either doubling or you're adding a point to its negative, then there's another cases, and then there's also one point which I haven't even talked about, which is a point infinity, which doesn't have any representation as x, y. So this whole thing is a total mess.
Is this going to be on the test?
Well, it's not on the test, but it's in your favorite crypto libraries, so you can only hope that whoever implemented this in your favorite crypto libraries got those cases right.
Something that's much nicer is that Montgomery shape. So this is actually what we recommend for doing Diffie-Hellman. A lot of people were at the keynote talk yesterday and heard Ian Goldberg talking about you can do a quick Diffie-Hellman and give yourself forward secrecy. And there's lots of applications of Diffie-Hellman. If you want to do Diffie-Hellman, then what we recommend is using Montgomery curves, or for instance, take an Edwards curve and view it as a Montgomery curve, which always works. Take a Montgomery curve and use what's called the Montgomery ladder. What's interesting about the Montgomery ladder, first of all, you only have to work with one coordinate instead of with two. So instead of working with both u and v or both x and y, you can work with just with u coordinate of a point. And that makes it very easy to just send a u coordinate through the network, and then your arithmetic you can make very small. And then there's a very simple procedure which figures out at the same moment n times a point and n plus 1 times a point, given the u coordinates there, starting from the point where the n and n plus 1 are computed from the same thing with half of n. So you take n and you divide it in half, you recursively figure out that half of n times p and half of n plus 1 times p, and then apply certain formulas which always work to give you n times p and n plus 1 times p. And the fact that that always works makes Montgomery curves really, really nice.
One last comment on the Montgomery slide. So those of you who have heard about the prime 25519 in other contexts, most of this will be about curve 25519, which is a Montgomery curve in exactly this shape. And that's the same curve that we showed you before, but yet another way of moving between those coordinates. So it's all the same mathematical object, but with different ways of presenting it. So curve 25519 is still our preferred curve. It's not that you should use this other curve because we said so. It's the same curve. There are other people who recommend using curves. So there's this whole long list of standards starting 1991. So remember, Victor Miller and also Neil Koblitz in 1985 suggested using elliptic curves. We've been quoting Victor Miller because he has this comment about index calculus, but it was the two of them at the same time. So a bunch of years later, standardization committees have caught up, and ANSI, the American standard, is the first one to propose elliptic curves. Meanwhile, there's also the Secure Curves Working Group in Canada, mostly with Certicom, and there's IEEE standards P1363 is actually explaining how to choose curves. Then NIST is proposing curves, ANSI is catching up, then there's a European or mostly German consortium called Brainpool. There's NSA Suite B after that, and then there's also in 2011 ANSI, which is not a typo, it's a French, well, they always have to have something special, so they stick in an extra S there. Now, there's this wonderful XKCD about, okay, there's 15 standards out there, we should really do something to merge them, and then, oh crap, now we have 16 standards. We also have a suggestion of how one should use secure curves, and well, to highlight what we mean by that, this is a web page called SafeCurves.cr.yp.to, and we evaluate security of curves there. And well, this talk gives you the rationale and some background on that.
Okay, so what do all these standards say, and what do we say about choosing curves? Actually, there's a lot of agreement. There's basically complete consensus on a lot of criteria, a lot of convergence. I mean, the research is saying the same thing about what's safe, except, well, you'll hear the exceptions later. First of all these standards will say, we're looking at elliptic curves, don't use something like the clock, so you have to have an elliptic curve. All the standards say you have to make sure that the number of curve points has a big prime divisor in it. And this is something else you can verify. It's not too hard to do this computation. So if somebody shows you an elliptic curve, you can figure out the number of curve points, and you can figure out that, oh yeah, there is a big prime inside it. Before, you were hearing about a curve where the prime for the field was around 2 to the 255, 2 to the 255 minus 19. The L for that one is something like 2 to the 252. Not exactly, it's some prime number around there. In general, if L is, say, 2 to the 200, the attacks that we have take time square root of L. That's how long it takes to break elliptic curve crypto, is square root of L simple operations. So if L is 2 to the 200 or bigger, that means it's at least 2 to the 100 operations to break. And that's a pretty serious number of operations. Now, we're more conservative, so we recommend taking L up at 2 to the 255 or 2 to the 256, or somewhere around there, and then it's like 2 to the 128 operations. That's massive computation. Some people would want L to be even bigger. There's nothing wrong with taking L even bigger if you can afford it. Last criterion there is that L must not have some weird relationship to the prime p that you were doing arithmetic mod p. So L is not allowed to divide p or p minus 1 or p squared minus 1 up to p to the 20 minus 1. Now the reason for this, it's not going to happen by accident, but if you made a curve that actually had this weird feature like L being p plus 1, which you can do, that would actually be something like a circle in disguise. That would be something you could transfer your curve to a circle, and that's kind of scary because we know circles, clocks are vulnerable to index calculus. So don't have L being one of these very special values.
And there's no point in stopping at 20. You can also go up to 1,000, but 20 is that thing where all standards agree. Then it's one thing where Not all standards agree, but it seems like a cautious thing to do to avoid unnecessary structure. In general, if you buy into a structure because it gives you the arithmetic speed up that you absolutely need, you're on a tiny 8-bit microcontroller and the only thing you can do is exactly this computation, okay, you get what you pay for. But if you're actually on a big computer and you're fighting over a fraction of a microsecond, you should avoid unnecessary structure. Also, yes, we're throwing away a large fraction of all curves, but in the end what you need is one good curve for the whole internet to communicate. So you can be selective. You do not need to have like the largest possible curve group that you can imagine. You just want to narrow it down to things that are non-scary. So some things are a little bit scary if the curves have a certain structure which is called a CM field. Then if you take a random curve out of the pot, even if it is a random curve out of the pot which have a large prime factor, then usually the thing which is called a discriminant is going to be pretty big. Also, it shouldn't have any special divisibility properties. Then I mentioned already, why stop at 20? How about we go up to 100 or go up to 1,000 or go up to something which is actually related to the security level. So if your L is like 200 bits, then okay, this is something very close to that. Why not just require that there is no such curve? So both the brain pool and our SafeCurves standard, or our SafeCurves page, is saying do not choose any suspicious curves. Just go for something which fits everywhere. Also, most of the standards, the NIST curves excluded, say that you should use a prime. In general, you could use a more arbitrary fine field, but primes feels like the comfortable, solid thing to do.
So if you're worried about all these things where maybe there's some attack that uses this structure, we don't know what the attack is, but let's just stay away from the structure just in case, then you should also think, what if there's some attack out there that we don't know, and the attacker has manipulated our choices of curves to be vulnerable to that attack. So it's kind of an obscure situation, but maybe there's some attack we don't know, like the attacks that maybe exist that exploit this structure. Not that anybody's been able to figure it out, but maybe there's an attack that breaks some curves, maybe 1 in a million or 1 in a billion curves, and we haven't figured it out, but maybe the bad guys have figured it out. The bad guys being, of course, the Chinese Advanced Persistent Threat Unit somewhere in Shanghai. Maybe the bad guys have figured it out, and maybe they've managed to manipulate the standardization of a curve to find a curve, which is actually, they're going to tell the rest of us, oh yeah, this is good. You don't know any attacks which break this, but they secretly know an attack that we haven't figured out. It's a very obscure corner case, but maybe this happens.
Well, let's look at what's out there. So the NIST curves are saying that their parameters, so they go for Weierstrass curves, x squared plus y squared equals x cubed minus 3x, so the minus 3 is explained because it's more efficient, and then plus b, where they say, okay, this b was generated verifiably random. Now, what they publish is a seed, which then, if you run it through SHA-1 as a hash function and do some arithmetic, will give you a b, which is the b in the standard. Now, is a seed actually random? Where does this thing come from? We don't know. We know who it was to generate the curves, but we don't know what he tried. Now, if somewhere in China, some of a different standard, not the goodness standard, there is somebody who is actually willing to run, say, 1 billion hash computation, 1 billion curve counts, then this person, if he knows like a very rare property of elliptic curves, like 1 in a billion, 1 in a trillion, then he has to try that many times, try different hashes, but in the end he just publishes the one hash which worked. This is the same that NIST does, because NIST publishes the one hash that gives them a prime order curve. Also NIST must have tried lots of curves till they found one which has a prime order. So it is not verifiable where this number comes from. Now, I keep making fun of the French, but sorry. So the French come up in 2011 and say, well, how about you use our curve? It's random. They don't even give you a seed, yeah?
Okay, better response from the Germans. So the Brain Pool project goes for something that we call rigidity. So what rigidity means is that the people, whatever process that it was that some people carried out to generate a curve that's standardized for everybody to use, If it's rigid, if that process is rigid, it means it can only have generated a small number of curves. So then if they're trying to find a curve that's satisfying some 1 in a billion property that allows some secret attack that we don't know, that they know, then they just don't have the flexibility to generate that curve. So a rigid curve generation process protects us against this corner possibility because it means the people who generated the curves couldn't have generated many different curves searching for one vulnerable to this attack. What Brainpool does, it's somewhat rigid, fairly rigid. What they say is you take the digits of pi, digits of e, in some pattern, feed them through some sort of hash function, and then that's what generates the number b. Now, they don't completely explain the hash that they're using. They don't say why they're using pi and e instead of using square root of 2 like some crypto standards do. It's basically a nothing up my sleeve number, except there's a little bit of weirdness to it. You can actually look at the Brainpool numbers and you see some very weird patterns where they said, oh yeah, actually we shouldn't have chosen that hash. Yeah, that was a bad idea. But okay, they had some little bits of flexibility in what they were doing, but not much. So
I think we could get skeptical if it was like e to the 2 pi square root of 13 over 15 times something, and then you get this long expression with pi and whatever. E and pi kind of okay. I mean, I was around back when we did the Brainpool curves, and pi and e seemed like innocent.
But square root of 2 and square root of 3 also seem innocent. There's a little bit of flexibility. What we recommend, so SafeCurves allows what Brainpool is doing. In the SafeCurves rating of different curves, what Brainpool does is okay. What we actually recommend, which is also allowed by SafeCurves, is to take the smallest numbers that satisfy all the criteria that are out there. So instead of taking some random number, you take the smallest number. And that gives you very, very little flexibility. As a curve generator, all you could possibly do is play with the criteria. But that's something where basically people have converged on, here's what the criteria are.
Then, so far we've talked about ECC security. DLP security. So somebody gives you a static problem, here is the base point, and here's what else has computed. You do not have access to any of the computation. Dan already mentioned timing attacks as something. That's one example of how real-world crypto gets broken. If you see like OpenSSL is broken in the elliptic curve case again, that's not because somebody was really smart and found a better algorithm, better than the square root of L that Dan just mentioned. It is because OpenSSL is leaking ways of how it's implemented. So somebody could feed you a point which is not actually on a curve, and depending on how your program is written, you just take this x and y, take your secret A and compute with it, and you output the result. And this might give the attacker some information about your A that otherwise you wouldn't have gotten. Or you leak timing information, or you get some very weird failure, say, oops, you have divided by 0. Now this shouldn't have happened with any legitimate point, but this point was not legitimate. And of course, well, if there's anything that doesn't happen normally, it's still something that an attacker could exploit. An attacker can handcraft a point for you which will give a particular failure if that bit is 1, and doesn't give you a failure if the bit is 0.
So if you change what your curves are, then remember from before with D being square or not square, that changes whether there's some failure cases that are hard to test for. Well, if you choose your curves carefully, then you end up with the simple implementations actually being correct, secure implementations. And that's a very good feature. It makes ECC much less fragile, much less likely to fail, much easier to implement in a secure way. And that's the main motivation for SafeCurves. That's the big difference between all the previous standards and what we're doing on the SafeCurves site, is SafeCurves says, here's all the standard criteria, plus here are extra criteria that make sure that your simple implementations are going to work correctly. Makes it much less fragile to implement ECC. And just one example is last, but twist security. So if you have, for instance, NIST P224 is not a twist secure curve. And if you have a curve that's not twist secure, and all the standards, everything before SafeCurves allows something like NIST P224, then there's something called twist attacks, which will break ladder implementations unless the implementer went to some extra work. Your random test will say, oh yeah, that implementation is fine. You do your regression test suite, everything seems fine. But then you didn't realize that you had to test what happens if somebody feeds you a U coordinate, which was not actually a coordinate of a point on a curve. It's a coordinate of, there's some other curve called the twist, and nobody actually checked anything about that. So unless the implementer went to some extra work, which is not obvious, which doesn't seem to have anything to do with functionality, these twist attacks really do break ECC. Now, the way to get around this is either tell the implementers, oh, it's your fault, do ECC better, you should test for this, we told you to test for this, why didn't you read page 472 of the spec,
Blame the implementer.
or you choose a better curve. And that's one of the SafeCurves extra requirements, is that you choose a curve where it is twist secure. And then if the implementer doesn't check, that's fine. If you're interested in more information, here's the last, flip over to the whole thing. This is just an excerpt from the SafeCurves website with our ratings of various curves, and then various other research. The green lines there are from us and other research groups that agree and have generated more curves meeting the criteria. So go to safecurves.cr.yp.to. Thanks for your attention.
So it seems like a question. Can you shout loudly? Okay. So the question was whether there is a proof that index calculus attacks wouldn't work on elliptic curves. What is there is a certain function called the height function, and both Victor Miller and then later on Jacobus in a paper called the height function, or it's a talk actually, height function and golden shield for elliptic curve, give arguments why if you take a curve and lift, then if you take the points there, you can't have enough points in your vector base to get relations. So it is not, what it is excluding is attack by lifting from elliptic curve over a field to the elliptic curve over the rationals. If anybody comes up with a very different way of index calculus, that's not excluded. Also, it's a paper about prime field curves. If you have a binary curve, this does not apply. Are there more questions? I mean, we're still around for a bit, so John is also walking around with a microphone.
There's some hand up on the left, all the way on the left. Sorry? URL is safecurves.cr.yp.to.
If you were building a CA today, just like an internal CA, and you had the ECC, the curve implementations that are in most browsers today, or RSA, which would you choose between? The broken curves that are in most browsers today, the NIST curves and things like that, or would you still rely on RSA?
Which is worse between the following bad options? Look, it's not like the NIST curves are completely broken. It is theoretically possible to do a safe implementation of the NIST curves. And for RSA, even though there's these index calculus attacks, you pump it up to really large key sizes, then we don't know any way to break that either. There's different risks either way, but moving forward, we're trying to make a better environment for people doing elliptic curve cryptography and public key cryptography in general and crypto in general, so that it's a lot easier to do secure implementations. And, well, if you're stuck with, for instance, what's supported in your browser, it's pretty much use NIST P256 and then work really hard to make sure that you're implementing that correctly. I would say there's a different kind of risk for RSA and for NIST P256. I mean, there's maybe both of them, the implementations are hard to get right. For NIST P256, there are issues of how were these seeds chosen, for instance. These are all small kind of risks, but, well, you have to watch out for them. Maybe I would say the biggest risk is not having a constant time implementation. That's a problem for both RSA implementations and NIST P256 implementations.
But I mean, pragmatically, I would push for getting elliptic curves in there, and then as a second step, replace the elliptic curve once the browsers and all the infrastructure is comfortable with having elliptic curves plugged in there.
Hey, so I'm curious, let's see, how these attacks relate to things like ECDSA, like actually doing signing. Like, are they the same kinds of attacks? Or?
So if you can do discrete logs, so computing LSSA from A times P, then you can also break ECDSA. So for the signature standard, there is a public key, same way that we showed here. We just stuck with Diffie-Hellman because it was somewhat conceptually easier to explain. Also in the signatures, you also get to see many more examples of discrete logs. For every signature, you see a nonce times the point. So if you can break that, you can also recover the long-term secret key. And then there's failures of people to get enough randomness. So there's attacks on ECDSA that actually do not break the discrete log problem, that are just working by, oops, somebody was using a very skewed random number generator, or like in the Sony PlayStation disaster, somebody was not using any randomness at all. So we have a proposal called ED 25519, which is a signature scheme using the curve we presented earlier. And it also not just has a better curve, it also has a better data flow of the encryption, so that things such as, well, skewed randomness or no randomness at all do not appear. So there's a hash function involved in hashing a secret, so you have pseudo-randomness, which is good in this case, and you don't need any fresh randomness per signature. Behind you.
Have you spent any time looking at the ECDSA implementation in more recent OpenSSH? Do you have any comments on their choice of curves and or implementation of things like susceptibility to constant time, or whether they were careful about constant time, et cetera?
So I haven't personally looked at the OpenSSH code. I believe that they've added support for our recommended curve, I don't know whether the implementation there is using one of our recommended constant time implementations. In general, variable time is a huge mess. I mean, any typical cryptographic implementation is broken by side channel attacks. So, I mean, getting past that is a huge problem for cryptography. And making it easier to do constant time implementations is one of the major motivations for this work. I just don't know the answer to your question about OpenSSH in particular.
So I don't know the answer either. However, so then it's saying it's easier to get it right. That's by the curve shape and by the, hey, if you're doing Montgomery arithmetic, the easiest way is to do the ladder. And of course, you can still screw up the data flow with ifs and else, but as a little advertisement, we have good implementations out there on the internet. So there is the SALT library, spelled NaCl, like the chemical symbol for salt, which does include constant time implementation of the curve 25519 for Diffie-Hellman, and will hopefully very soon also include the ECDSA version, so our ECDSA version at 25519 in constant time. We have optimized versions like with assembly, and we have reference versions. What's common to those is that they all use the constant time, that they all avoid branches. The optimized ones are faster.
And this is also, if you look at applications that are using our recommended curves, then, for instance, iPhones or Tor or TextSecure, these are typically using the software that we produce as well.
So on with SALT, you brought it up, a lot of people have been having a heck of a time trying to get SALT to compile on anything other than apparently your personal machines. Which, you know, is fine. I mean, like, Lord knows I've written C that doesn't compile anywhere else. That's not a problem. But any comments on something like libsodium or the other more portable SALT projects? Have you looked at the implementations there so we can get it to work with, like, Ruby or stuff?
Yeah, so libsodium took the reference implementations we provided, repackaged those with an autoconf type build script, and then later on added a few of the optimized assembly implementations, which is, I mean, it's a perfectly reasonable structure. We're not tied to any particular build system. There's also a new project we have called TweetSalt. So if you go to twitter.com/TWEETNACL, then you see 100 tweets, which is function for function compatible with SALT and provides all the same functions, high security implementations of elliptic curve cryptography and all the necessary secret key cryptography. And that's something where, you know, 100 tweets, it's not that much code. You just drop the .c into whatever application. Of course, you could also compile that with an autoconf type build system. I think in general, so libsodium has added some things which we haven't reviewed and can't vouch for those things, but to the extent that it's just repackaging the implementations that we provide, yeah, that's fine. We are very careful with making sure for things like constant time that we're avoiding as much as we can of GCC and, well, CLang and so on, messing things up. So we try to do reviewed assembly implementations of things, in part to avoid having the compiler as part of our trusted tool chain. But this isn't a big issue. I mean, there's not that much risk that the compiler screws things up. And if you have somebody who's taking some of our reference C code and using that's fine.
And one last question from a user on the stream is Mayukuchu asks, which of the SafeCurves do you think would be fastest to implement at 128, 192, and 256-bit security?
Sorry?
Could you repeat the security level, please?
At 128-bit, 192-bit, and 256-bit security.
Okay, so up until here and then upwards is 128, and the top ones are a little smaller. So there is two curve proposals by, well, then Mark Hamburg, Anna Krasnova, and me, and this one is Dan's Curve 2519. Both of those are fine. We also have, well, this one was constructed because we wanted one for P going to 3 mod 4. I think more people have looked at the 25519. There's more implementations out there, so I would stick with that one. For the security level of 192 bits, well, shameless self-promotion.
Yeah, okay, so upon request from Silent Circle, we generated a curve which uses a 414-bit prime. It's x squared plus y squared equals 1 plus 3617 x squared y squared. Because it's a 414-bit prime, it's more than a 2 to the 200 security level, but it's as fast as, say, NIST P384, even faster than NIST P384. So if you're interested in the 192-bit security level, then, well, ours goes up to 11. And then, yeah, for the higher security level, the slide is truncated, but 3 groups independently have all agreed on a curve that's called E521, which is a certain curve mod 2 to the 521 minus 1, and that's a prime number. And if you can afford a curve up at that level, then yeah, go for that. And that one, I don't know if anybody's implemented it yet, but it should be easy to implement in a secure way, and it should have well, it has all of the security properties that we verified. It should have performance very similar to the other curves up at that security level. So if you can afford that, then definitely go for E521. I guess if there's other questions, then we'll be sticking around for a bit. So happy to answer those, and otherwise, thanks for your attention.
And to the 170 for the bigger system. Now, when RSA was designed, the linear CIF has just come out, so that reduced the security to something like 2 to the 110, which is still pretty big. So RSA 1024, where the government now tells you don't use this anymore, at that time looked like 2 to the 110 operations. That's independent of the computer architecture. This is just mathematical operations. If you go for say, bit operations or computer instructions, it's a multiple of that. But then the algorithms just then mentioned have brought the security down to something like 2 to the 80 or to the 112, depending on the size of your RSA key. In the middle of this, even before the number-filled CIF came out, Victor Miller was proposing to use elliptic curves. So there was a Crypto 1985 paper where he proposes use elliptic curves, and one of the arguments he gives for this is that mathematically it doesn't look like there could be anything like these index calculus attacks. So closest to elliptic curve cryptography would be, say, Diffie-Hellman in defined fields, and there's an extensive use of making, well, defined field look like the integers. There's some sort of, yeah, it's called lifting, and Victor shows that, okay, lifting wouldn't exist for elliptic curves.
All right, so to get an idea of what elliptic curve crypto looks like, we actually have a little warm-up here with the simplest kind of curves you can imagine. Well, you could maybe think about straight lines, but okay, if you don't have a straight line, maybe the simplest curve you can imagine is a clock, or mathematically a circle. So this is x squared plus y squared equals 1. Take all the points x comma y in the plane that satisfy x squared plus y squared equals 1. That's the unit circle. Now, I have to give you a warning here, which is that circles are examples of ellipses. Ellipses are stretched circles. And you might think when you hear elliptic curves, that's just another name for ellipses, but that's not the situation. Ellipses and circles are not elliptic curves. Elliptic curves are just a little bit more complicated than circles. So when I show you a circle, or if I stretched it, made it an ellipse, that would not be an elliptic curve. And any advantages that elliptic curves have, ellipses and circles don't have that advantage.
Okay, just in case somebody has forgotten what these things look like. It's kind of quaint, you know. So some examples of points on the clock. So when you look at this well, pocket watch, then you find the 12 o'clock points.
Suddenly, the late 1970s, there was the original Diffie-Hellman public key system and RSA, and that attracted a lot of attention to how fast can we factor numbers, how fast can we compute discrete logs, and people started really developing this index calculus idea. A lot of the buzzwords are listed here, like the linear sieve, the quadratic sieve, the number field sieve, the function field sieve. I should mention that some of these recent, the last few lines in this history listed here for the function field sieve, that's not something which helps for factoring. It's only for discrete logs. But it's still within this index calculus umbrella. It's something which is a really terrifying attack algorithm. If you're trying to figure out how big do your RSA keys have to be, then you have to get into understanding this really complicated series of algorithms, and you have to worry there's going to be more improvements.
So to give you a numerical example of how smaller your security level gets, if you fix your key size, say RSA with 1024 bits or 248 bits, then in the initial, when they designed the system, they understood CFRAG, and the linear sieve was just coming out. So these systems for CFRAG would have a security level. It would take an attacker 2 to the 120 operations to break it. For the smaller system,
Bernstein and Tanya Lange talking about SafeCurves, their new mechanism for choosing safe elliptic curve cryptographic curves.
Thank you very much.
thanks. So a few quick words on, am I audible? Okay. So a few quick words on public key cryptography, so where elliptic curves fit in there. So SafeCurves, the curves stand for elliptic curves in there. And that is part of public key cryptography, so something that you use when you're signing, say you're a government, you're issuing e-passports, or CA, you're issuing certificates, or you're doing code signing. If you do that, then you're using public key cryptography and elliptic curves and RSA and also Diffie-Hellman signature, well, fine field-based signatures, DSA, are typical examples. Also, public key encryption, so when you're making a connection to a website, the first thing you do is you do a handshake. Well, assuming you do the proper thing with HTTPS, the first thing you do is you make a cryptographic handshake, and you have met the web page before, so you're building up a shared secret based on public key cryptography. RSA is also an encryption system, then elliptic curve Diffie-Hellman and normal Diffie-Hellman and fine fields are typical examples. And this is to be contrasted with symmetric cryptography, which you use for, say, bulk encryption. So if you do your full disk encryption, you don't want to do public key encryption because it's much slower. So AES and SALSA20 are examples of a system where both parties, you and the hard disk, or you and the website that you've now shared a key with, know the same secret and then can transmit, encrypt the data very, very quickly.
All right, I'll give this one a try. So within public key crypto, why are people moving from RSA to elliptic curve cryptography? The main reason is because of an attack strategy called index calculus. Now, this is a complicated attack. It's something which keeps getting more and more sophisticated over the years. It started in the 1930s, before crypto was really understood. In the 1930s, people were thinking about how do we factor big numbers, and they started with the beginnings of index calculus. And then, well, okay, after that, in the 70s, people were still thinking about factorization. There's a CFRAC algorithm, and then